This example takes steady state, one-dimensional conduction with no heat generation. So here's our differential equation, and solves for both temperature and heat transfer rate as well as flux using different boundary conditions. So the first thing we're going to assume is that K is constant. It is not a function of X. And so that leaves us with d squared T dx squared equals 0. So because we have a second order equation, the T varies with X, we need two boundary conditions. So boundary conditions are when you're working with something as a function of length, like X. And so our conditions have to be at X equals something, T equals something. But we're going to just take this and integrate it so that we have it in terms of constants. So the first thing we do is integrate d squared T dx squared, and we come out with dt dx, first order, equals a constant, since we didn't specify any particular boundaries. And then we do it again, and we find that T of X equals C1 of X plus C2. So this is what it's always going to look like if you have one-dimensional steady-state conduction with no generation. The changes, or the reason that we have different temperature distributions, is boundary conditions to solve for C1 and C2. So let's take case 1. Let's say at X equals 0, T equals TS1. At X equals L, T equals TS2. So this is the simplest case we have. So if we take our temperature distribution and put X as 0, and our T is TS1. So if X is 0, C1 is 0, so that means C2 is TS1. Now we use the second boundary condition. At X equals L, T equals TS2. So TS2, where I'm putting that in for T of X, equals C1 times L, because X is L, plus C2, which we already solved for. And so our C1 is going to equal TS2 minus TS1 divided by L. And finally, because this is what we're looking for is our T of X, we put our constants back in. So this is TS2 minus TS1. Remember, C1 is multiplied by X, so often what we do is go X divided by L, plus our C2, which is TS1. So if we were trying to find Q, it equals minus Ka dt dx. We've already solved for dt dx right up here. So dt dx is just C1, and C1 is TS2 minus TS1 over L. So this is going to equal minus Ka TS2 minus TS1 over L. If we wanted to find the heat flux, all we do is do the same thing without the area, because heat flux is per area over L. All right, let's look at something that's a little bit different. So what we're going to look at is we're going to have the same t of x, but now we're going to change the boundary conditions. We're going to still say at x equals 0, t equals ts, but now instead at x equals L, minus k dt dx equals h TL minus t infinity. So let's go back to our t of x and put in some boundary conditions. So at x equals 0, when we go back to our t of x, and our t of x that I'm looking at is right here, we have the exact same thing as we had before. Ts equals c1 times x, which is 0, plus c2. So our c2 is just ts. Now we look at our second boundary condition. At x equals L, again, minus k dt dx equals h TL minus t infinity. So let's put that back into our t of x equation. We know, again, that dt dx, we've found it before, is going to equal c1. So what is our c1? So we look over here, dt dx equals minus h over k TL minus t infinity. So that's going to equal our c1. We go back to our t of x. So our t of x equals c1 minus h over k TL minus t infinity times x plus c2, which was ts. So again, if we want to find our q, it's minus ka dt dx. So it's h a TL minus t infinity. If we want to find q prime, it's just h TL minus t infinity.